Hello. Here you will learn the theoretical basis of forecast and how to calculate the forecast using different techniques by solving an example and some problems. The work presented here is based on Chapter 3 of the Operations Management book William Stevenson wrote and published by McGraw-Hill. Before starting, if you did not do yet, subscribe and activate the alarm to be notified of the new videos. In the following few minutes, you will learn the meaning, importance, common features, elements, and steps of the forecast.
To estimate what is judged likely to happen in the future, especially in connection with a particular situation and based on some knowledge or data, is called forecasting. For example, the weather forecasting when they say it is going to rain later today. Another example, in business they forecast the sales, or it is called the demand, of a coming period of time. Forecasting is an important topic for engineering and business students because forecasts are a basic input in the decision processes of operations management because they provide information on future demand. The primary goal of operations management is to match supply to demand. Having a forecast of demand is essential for determining how much capacity or supply will be needed to meet demand. For instance, operations needs to know what capacity will be needed to make staffing and equipment decisions. Budgets must be prepared, purchasing needs information for ordering from suppliers, and supply chain partners need to make their plans. Two aspects of forecasts are important. One is the expected level of demand, the other is the degree of accuracy that can be assigned to a forecast. Many forecasting techniques are in use and of course, they are quite different from each other, as you shall soon discover. Nonetheless, certain features are common to all, and it is important to recognize them. These common features are: 1. Forecasting techniques generally assume that the same underlying causal system that existed in the past will continue to exist in the future. 2. Forecasts are not perfect, actual results usually differ from predicted values. So, allowances should be made for forecast errors. 3. Forecasts for groups of items tend to be more accurate than forecasts for individual items because forecasting errors among items in a group usually have a canceling effect. Opportunities for grouping may arise if parts or raw materials are used for multiple products or if a product or service is demanded by a number of independent sources. 4. Forecast accuracy decreases as the time period covered by the forecast, the time horizon increases. Generally speaking, short-range forecasts must contend with fewer uncertainties than longer-range forecasts, so they tend to be more accurate. To make a forecast, the following 6 basic steps should be followed. The first step is to determine the purpose of the forecast. Like, how will it be used and when will it be needed? This step will provide an indication of the level of detail required in the forecast, the amount of resources, personnel, computer time, dollars, that can be justified, and the level of accuracy necessary. The second step is to establish a time horizon. The forecast must indicate a time interval, keeping in mind that accuracy decreases as the time horizon increases. While the third step is to obtain, clean, and analyze appropriate data. Obtaining the data can involve significant effort. Once obtained, the data may need to be cleaned to get rid of outliers and obviously incorrect data before analysis. After that you have to select a forecasting technique. Then make the forecast. Finally the forecast has to be monitored to determine whether it is performing in a satisfactory manner. If it is not, re-examine the method, assumptions, validity of data, and so on. Modify as needed, and prepare a revised forecast.
Now let us move to the different approaches and techniques used for the forecast.
There are 2 general approaches to forecasting, quantitative and qualitative. Quantitative methods involve either the projection of historical data or the development of associative models that attempt to utilize causal, explanatory, variables to make a forecast. Quantitative techniques consist mainly of analyzing objective, or hard, data. They usually avoid personal biases. The quantitative techniques are mainly classified either to time series forecasts and associative models. These techniques will be explained soon. Qualitative methods consist mainly of subjective inputs, which often defy precise numerical description. Qualitative techniques permit inclusion of soft information, as human factors, personal opinions, and hunches, in the forecasting process. Those factors are often omitted or downplayed when quantitative techniques are used because they are difficult or impossible to quantify. The qualitative approach is used in the situations where management must have a forecast quickly. There may not be enough time to gather and analyze quantitative data. At other times, especially when political and economic conditions are changing, available data may be obsolete and more up-to-date information might not yet be available. Similarly, the introduction of new products and the redesign of existing products or packaging suffer from the absence of historical data that would be useful in forecasting. In such instances, forecasts are based on executive opinions, consumer surveys, opinions of the sales staff, and opinions of experts. Now, let us focus on the first category of quantitative forecast, which is a time series forecast. A time series is a time-ordered sequence of observations taken at regular intervals, for example, hourly, daily, weekly, monthly, quarterly, annually. The data may be measurements of demand, earnings, profits, shipments, output, or productivity. Forecasting techniques based on time series data are made on the assumption that future values of the series can be estimated from past values. Although no attempt is made to identify variables that influence the series, these methods are widely used, often with quite satisfactory results. Analysis of time series data requires the analyst to identify the underlying behavior of the series. This can often be accomplished by plotting the data and visually examining the plot. One or more patterns might appear: trends, seasonal variations, cycles, or variations around an average. In addition, there will be random and perhaps irregular variations. These behaviors can be described as follows. Trends refer to a long-term upward or downward movement in the data. Population shifts, changing incomes, and cultural changes often account for such movements. Seasonality refers to short-term, fairly regular variations generally related to factors such as the calendar or time of day. Restaurants, supermarkets, and theaters experience weekly and even daily seasonal variations. Cycles are wave-like variations of more than 1 year's duration. These are often related to a variety of economic, political, and even agricultural conditions. The variations may be irregular or random variations. The irregular variations are due to unusual circumstances such as severe weather conditions, strikes, or a major change in a product or service. They do not reflect typical behaviors, and their inclusion in the series can distort the overall picture. Whenever possible, these should be identified and removed from the data. While the random variations are residual variations that remain after all other behaviors have been accounted for.
Here various techniques for the analysis of time series data will be described. But before turning to those discussions, one point should be emphasized: a demand forecast should be based on a time series of past demand rather than unit sales. Sales would not truly reflect demand if one or more stockouts occurred.
Now let us start learning how to calculate the forecast. The first technique we will study is called naive method. A simple but widely used approach to forecasting is the naive approach. A naive forecast uses a single previous value of a time series as the basis of a forecast. The naive approach can be used with a stable series of variations around an average, with seasonal variations, or with trend. With a stable series, the last data point becomes the forecast for the next period. Thus, if demand for a product last week was 20 cases, the forecast for this week is 20 cases. With seasonal variations, the forecast for this season is equal to the value of the series last season. For example, the forecast of the number of checks cashed at a bank on the first day of the month next month is equal to the number of checks cashed on the first day of this month. For data with trend, The forecast is equal to the last value of the series plus or minus the difference between the last two values of the series. For example, suppose the last two values were 237 and 243. The difference between them is 6. So, the next forecast would be 243 plus 6 equal 249. Although at first look the naive approach may appear too simplistic, it is nonetheless a legitimate forecasting tool. Consider the advantages: it has virtually no cost, it is quick and easy to prepare, and it is easily understandable. The main objection to this method is its inability to provide highly accurate forecasts. However, if resulting accuracy is acceptable, this approach deserves serious consideration. Moreover, even if other forecasting techniques offer better accuracy, they will almost always involve a greater cost. The accuracy of a naive forecast can serve as a standard of comparison against which to judge the cost and accuracy of other techniques. Thus, managers must answer the question, is the increased accuracy of another method worth the additional resources required to achieve that accuracy? The second group of techniques is the techniques of averaging. They are used when the historical data contain a certain amount of random variation that tends to vague systematic movements in the data. This randomness arises from the combined influence of many relatively unimportant factors, and it cannot be reliably predicted. Averaging techniques smooth variations in the data. Averaging techniques generate forecasts that reflect recent values of a time series. These techniques work best when a series tends to vary around an average. 3 techniques for averaging are described, which are moving average, weighted moving average, and exponential smoothing. One weakness of the naive method is that the forecast just traces the actual data, with a lag of 1 period. It does not smooth at all. But by expanding the amount of historical data a forecast is based on, this difficulty can be overcome. A moving average forecast uses a number of the most recent actual data values in generating a forecast. The moving average forecast can be computed using the following equation. Ft equals summation of At minus I divided by n, where Ft is the forecast for time period t. A t minus I is the actual value in period t minus I. And n is the number of periods in the moving average. Example for the moving average. Compute the forecast for period 6 using the 3-period moving average method given demand for cell phone for the last 5 periods. The last 3 periods are period numbers 3, 4 and 5. And the corresponding demands are 43, 40 and 41. The average of these 3 numbers is the forecast for period 6. So, the forecast for period 6, F6, is 41 cell phone. If actual demand in period 6 turns out to be 38, the 3-period moving average forecast for period 7 would be the average of the demands of periods 4, 5 and 6. That is 40. Note that in a moving average, as each new actual value becomes available, the forecast is updated by adding the newest value and dropping the oldest and then recomputing the average. Consequently, the forecast moves by reflecting only the most recent values. The advantages of a moving average forecast are that it is easy to compute and easy to understand. A possible disadvantage is that all values in the average are weighted equally. For instance, in a 10-period moving average, each value has a weight of 1/10. Hence, the oldest value has the same weight as the most recent value. If a change occurs in the series, a moving average forecast can be slow to react, especially if there are a large number of values in the average. To overcome such disadvantage, the weighted moving average is used. A weighted average is similar to a moving average, except that the most recent values in a time series is assigned more weight. For instance, the most recent value might be assigned a weight of 0.5, the next most recent value a weight of 0.3, and the next after that a weight of 0.2. Note that the weights must sum to 1. The weighted average forecast is calculated using this equation. FT equals WT multiplied by AT plus WT minus 1 multiplied by AT minus 1 plus WT minus N multiplied by AT minus N, where WT is the weight for the period T, WT minus 1 is the weight for period T minus 1, etc. A T is the actual value in period T, a T minus 1 is the actual value for period T minus 1, etc. Example for calculating the weighted average forecast. For the given data, compute a weighted average forecast for period 6 using a weight of 0.4 for the most recent period, 0.3 for the next most recent, 0.2 for the next, and 0.1 for the next. So using the previous equation, F6 equals W5A5 plus W4A4 plus W3A3 plus W2A2. So, F6 equals 0.4 multiplied by 239 plus 0.3 multiplied by 242 plus 0.2 multiplied by 240 plus 0.1 multiplied by 238, which equals to 240. So the forecasted demand for period 6 using the weighted average equals 240. The advantage of a weighted average over a simple moving average is that the weighted average is more reflective of the most recent occurrences. However, the choice of weights is somewhat arbitrary and generally involves the use of trial and error to find a suitable weighting scheme. The third technique of averaging is the exponential smoothing. Exponential smoothing is a sophisticated weighted averaging method that is still relatively easy to use and understand. Each new forecast is based on the previous forecast plus a percentage of the difference between that forecast and the actual value of the series at that point. That is, next forecast equals previous forecast plus alpha multiplied by actual demand minus previous forecast, where actual demand minus previous forecast represents the forecast error and alpha is a percentage of the error. More concisely, FT equals FT minus 1 plus alpha multiplied by a T minus 1 minus FT minus 1, where FT is the forecast for period T, FT minus 1 is the forecast for the previous period, that is, period T minus 1. Alpha is the smoothing constant, percentage. A T minus 1 is the actual demand or sales for the previous period. The smoothing constant alpha represents a percentage of the forecast error. Commonly used values of alpha range from 0.05 to 0.50. Low values of alpha are used when the underlying average tends to be stable. Higher values are used when the underlying average is susceptible to change. Here is an example for the smoothing average. Suppose the previous forecast was 352 units, actual demand was 365 units, and alpha equals 0.2. The new forecast would be computed as follows. FT equals 352 plus 0.2 multiplied by 365 minus 352 equal 354.6, which approximately equal to 355 units. Exponential smoothing should begin several periods back to enable forecasts to adjust to the data, instead of starting one period back. A number of different approaches can be used to obtain a starting forecast, such as naive approaching the average of the first several periods.
Another technique of quantitative forecasting techniques is the technique of trend that will be described now.
Analysis of trend involves developing an equation that will suitably describe trend, assuming that trend is present in the data. The trend component may be linear, parabolic, exponential, or growth curve trend. There are two important techniques that can be used to develop forecasts when trend is present. One involves use of a trend equation, The other is an extension of exponential smoothing. For the trend equation, a linear trend equation has the form ft equal a plus b multiplied by t, where ft is the forecast for period t, a is the value of ft at t equals 0, b is the slope of the line, t is the specified number of time periods from t equals 0. The coefficients of the line, a and b, are based on the following two equations. For example, consider the trend equation ft equals 45 plus 5 tons. The value of ft when t equals 0 is 45, and the slope of the line is 5, which means that, on the average, the value of ft will increase by 5 units for each time period. If t equal 10, the forecast, f10, is 45 plus 5 multiplied by 10 equals 95 units. An example for the trend line. Cell phone sales for a store over the last 10 weeks are tabulated below. Plot the data, and visually check to see if a linear trend line would be appropriate. Then determine the equation of the trend line, and predict sales for weeks 11 and 12. A plot suggests that a linear trend line would be appropriate. To calculate the coefficient of the line using these equations, we have to calculate both t multiplied by y and t to the power 2. Here is the table after calculating t, y and t to the power 2. The next step is to calculate the summation of the values of t, y, and t to the power 2. Now, substituting in the equation of b gives value of b equals 16.6. And substituting in the equation of a gives value of a equal 409.5. So the linear equation is ft equal 409.5 plus 16.6t. Now let's go back to see what is required. It is required to predict the sales for weeks 11 and 12. To predict the sales for weeks 11, simply substitute in the equation by t equal 11. So, f11 equal 409.5 plus 16.6 multiplied by 11 equal 592.1. Approximated to unit to be 592 unit. While for week 12, f12 equal 409.5 plus 16.6 multiplied by 12 equals 608.7. Approximated to unit to be 609 unit. In another video I will show you how to solve such problems by spreadsheets or scientific calculators. We still with the techniques of trend. The second one is the extension of exponential smoothing. A variation of simple exponential smoothing can be used when a time series exhibits a linear trend. It is called trend-adjusted exponential smoothing or, sometimes, double smoothing, to differentiate it from simple exponential smoothing, which is appropriate only when data vary around an average or have step or gradual changes. If a series exhibits trend, and simple smoothing is used on it, the forecasts will all lag the trend. If the data are increasing, each forecast will be too low. If decreasing, each forecast will be too high. The trend-adjusted forecast or TAF is composed of two elements, a smoothed error and a trend factor. So, TAF t plus 1 equals st plus dt, where st is the previous forecast plus smoothed error, and can be calculated by this equation. St equal TAF t plus alpha multiplied by at minus TAF t, while tt is the current trend estimate, and can be calculated by this equation. Tt equal tt minus 1 plus beta multiplied by TAF t minus 1 minus tt minus 1, where alpha is the smoothing constant for average, and beta is the smoothing constant for trend. In order to use this method, one must select values of alpha and beta, usually through trial and error, and make a starting forecast and an estimate of trend. Example for the trend-adjusted exponential smoothing. Using the cell phone data from the previous example, use trend-adjusted exponential smoothing to obtain forecasts for periods 6 through 11, with alpha equals 0.5 and beta equals 0.5. Well, the first required forecast is TAF6. So, t plus 1 equals 6. Applying the trend-adjusted exponential smoothing equation, TAF6 equals S5 plus D5. And S5 equal TAF5 plus alpha multiplied by A5 minus TAF5. Then it is required to estimate the trend at period t equals 5 and TAF5 as well. A net change of 54 for the three changes from period 1 to period 4, for an average of 18 that is the initial estimate of trend is based on. Thus, T5 equals 18. Notice that an initial estimate of trend is estimated from the first four values and that the starting forecast, TAF5, is developed using the previous actual sales, a 4, value of 474 plus the initial trend estimate. So, TAF5 equal 474 plus 18 equal 492. Now, S5 can be calculated using the values of TAF5, alpha and A5. S5 equal 492 plus 0.5 multiplied by 497 minus 492. This equal 494.5. To calculate the forecast for period 6, TAF6, using this equation. TAF6 equal 494.5 plus 18 equal 512.5 approximately equal 513. The next task is to calculate the forecast of period 7 TAF7. So, t plus 1 equals 7. Applying the trend-adjusted exponential smoothing equation, TAF7 equal S6 plus D6. Where S6 equal TAF6 plus alpha multiplied by A6 minus TAF6. Using the values of TAF6, alpha and A6. S6 equal 513 plus 0.5 multiplied by 501 minus 513. This equal 507. While T6 equal T5 plus beta multiplied by TAF6 minus TAF5 minus D5. That is T6 equal 18 plus 0.5 multiplied by 513 minus 492 minus 18 equal 19.5. To calculate the forecast for period 7, TAF7, using this equation. TAF7 equal 507 plus 19.5 equal 526.5 approximately equal 527. So the forecast of period 7 using trend-adjusted exponential smoothing equation. TAF7 equal 527. Similarly, we can calculate the forecast of period 8 TAF8, where t plus 1 equals 8. Applying the trend-adjusted exponential smoothing equation, TAF8 equal S7 plus D7, where S7 equal TAF7 plus alpha multiplied by A7 minus TAF7. Using the values of TAF7, alpha and A7. S7 equal 527 plus 0.5 multiplied by 520 minus 527. This equal 523.5. While T7 equal T6 plus beta multiplied by TAF7 minus TAF6 minus D6. That is T7 equal 19.5 plus 0.5 multiplied by 527 minus 513 minus 19.5 equals 16.75. To calculate the forecast for period 8, TAF8, using this equation. TAF8 equal 523.5 plus 16.75 equal 540.25 approximately equal 540. So, the forecast of period 8 using trend-adjusted exponential smoothing equation. TAF8 equal 540. In the same way the forecast for periods 9, 10 and 11 can be calculated known that alpha equals 0.5, beta equals 0.5, and using these three equations. The value for TAF9 is 558, TAF10 equal 570 and TAF11 equal 592. Unlike a linear trend line, trend-adjusted smoothing has the ability to adjust to changes in trend. Of course, trend projections are much simpler with a trend line than with trend-adjusted forecasts, so a manager must decide which benefits are most important when choosing between these two techniques for trend. Here, I will describe how to use the seasonality techniques. Seasonality means an irregular variation in the sales in a certain period of time or a certain season. Seasonality may be annual, monthly, weekly or even daily variations. Examples of seasonality are weather variations like sales of winter and summer clothes, vacations or holidays like airline travel visitors at tourist and resort centers. Rush hour traffic occurs twice a day, incoming in the morning and outgoing in the late afternoon. And theaters and restaurants often experience weekly demand patterns, with demand higher later in the week. Seasonality in a time series is expressed in terms of the amount that actual values deviate from the average value of a series. If the series tends to vary around an average value, then seasonality is expressed in terms of that average or a moving average. If trend is present, seasonality is expressed in terms of the trend value. There are two different models of seasonality, additive and multiplicative. In the additive model, seasonality is expressed as a quantity, which is added to or subtracted from the series average in order to incorporate seasonality. In the multiplicative model, seasonality is expressed as a percentage of the trend amount, which is then used to multiply the value of a series to incorporate seasonality. In practice, businesses use the multiplicative model much more widely than the additive model, because it tends to be more representative of actual experience, so we shall focus exclusively on the multiplicative model. The seasonal percentages in the multiplicative model are referred to as seasonal relatives or seasonal indexes. Suppose that the seasonal relative for the quantity of toys sold in December at a store is 1.7. This indicates that toy sales for that month are 70% above the monthly average. A seasonal relative of 0.85 for April indicates that April sales are 15% lower than the monthly average. Knowledge of seasonal variations is an important factor in retail planning and scheduling. Moreover, seasonality can be an important factor in capacity planning for systems that must be designed to handle peak loads. Knowledge of the extent of seasonality in a time series can enable one to remove seasonality from the data in order to distinguish other patterns or the lack of patterns in the series. Thus, one frequently reads or hears about seasonally adjusted unemployment and seasonally adjusted personal income. Seasonal relatives are used in two different ways in forecasting. One way is to deseasonalize data, the other way is to incorporate seasonality in a forecast. Deseasonalizing data is to remove the seasonal component from the data in order to get a clearer picture of the non-seasonal components, for example, trend. Deseasonalizing data is accomplished by dividing each data point by its corresponding seasonal relative. Incorporating seasonality in a forecast is useful when demand has both trend, or average, and seasonal components. Incorporating seasonality can be accomplished in this way. First, obtain trend estimates for desired periods using a trend equation. Then add seasonality to the trend estimates by multiplying these trend estimates by the corresponding seasonal relative, assuming a multiplicative model is appropriate. Example for seasonality multiplicative model. A shop owner wants to estimate demand for the next 2 quarters for a certain product. Sales data shown in this table consists of trend and seasonality. Known that quarter relatives are 1.2 for the first quarter, 1.1 for the second quarter, 0.75 for the third quarter, and 0.95 for the fourth quarter. Deseasonalize sales for quarters 1 through 8. After that, using the appropriate values of quarter relatives and the equation FT equals 124 plus 7.5 T for the trend component, estimate demand for periods 9 and 10. To deseasonalize the data, each quarter sales has to be divided by its corresponding relative. It is clear that the resultant deseasonalized data are increasing regularly and can be expressed by linear trend. The trend equation is given, so we can use it to calculate the sales for periods 9 and 10. Thus F9 equal 124 plus 7.5 multiplied by 9 equal 191.5. And F10 equal 124 plus 7.5 multiplied by 10 equal 199. Now, we have to multiply them by the seasonality relative to find the seasonal forecast for them, known that period 9 represents the first quarter while period 10 represents the second one. Thus, the demand estimate for period 9 equal 191.5 multiplied by 1.2 equal 229.8. While the demand estimate for period 10 equal 199 multiplied by 1.1 equal 218.9. In this example the seasonality relative is given. What if it is not? How to calculate the seasonality relative? The simple average method is used to calculate seasonal relatives. Each seasonal relative is the average for that season divided by the average of all seasons. Let us illustrate this method using the given data in the previous example, assuming that we have data for 4 more periods, so we have data for 12 periods. The first step is to find the average of each season. So, calculate the average for season 1, which is quarter 1. The average for season 2, which is quarter 2. The average for season 3, which is quarter 3. And the average for season 4, which is quarter 4. After that the average of the all seasons has to be calculated. Then, to obtain the seasonality relative for each season, divide the season average by the average of all seasons. Thus, the seasonality relative of the first quarter equal 183 divided by 153.5 equal 1.19. The seasonality relative of the second quarter equal 168 divided by 153.5 equal 1.1. The seasonality relative of the third quarter equal 116 divided by 153.5 equal 0.75. And the seasonality relative of the fourth quarter equal 147 divided by 153.5 equal 0.95. This is how to find the seasonality relatives, to use them to deseasonalize the data, then calculate the forecast for a certain season.
After learning different approaches and techniques used for forecasting, let us solve some problems.
Before starting the first problem, if you did not yet, subscribe and activate the alarm to be notified with the new videos. The first problem. The shown table shows the number of complaints received by a customer service department in the last 5 weeks. Prepare a forecast for week 6 using each of these approaches. The appropriate naive approach. A 3-period moving average. A weighted average using weights of 0.5, most recent, 0.3, and 0.2. Exponential smoothing with a smoothing constant of 0.4, known that the forecast for week 5 was 59. Recalling the 6 basic steps to make a forecast that were explained in the first video of this series. The first step is to determine the purpose of the forecast, is out of the scope of problem solving for training purpose. The second step is to establish a time horizon, which is given here in this problem to be weekly. While the third step is to obtain, clean, and analyze appropriate data. The data is already given, what we have to do is to plot them to check if they have a trend or vary around an average value. And we will start with this step. The fourth step is to select a forecasting technique. We already asked to make the forecast with different techniques for the purpose of training. The next step is to make the forecast. And finally, to monitor the forecast, but we did not learn it yet. So, we will go through 2 steps only. Plotting and examine the data, then making the forecast. The plotted data shows that variations around an average exist, and there is no trend or cycles. So, let us move to the next step to make the forecast using different techniques. The first one is to make the forecast using the appropriate naive approach. Since the data vary around an average, so, the forecast for week 6 equals the actual number of complaints in week 5, or F6 equal A5. So, F6 equals 64. The second requirement is to calculate the forecast for week 6 using the 3-period moving average. This means using the most recent 3 weeks, which are 5, 4, and 3. So, F6 equals A5 plus A4 plus A3 divided by 3. This equals 64 plus 58 plus 55 divided by 3 equal 59. The next is to calculate the forecast for week 6 using a weighted average using weights of 0.5, 0.3, and 0.2. The highest weight is assigned to the most recent period, which is week 5, the weight of 0.3 for the previous period, week 4, and the lowest weight is for week 3. So, F6 equals 0.5 multiplied by A5 plus 0.3 multiplied by A4 plus 0.2 multiplied by A3. Substituting by the values of A5, A4, and A3. F6 equals 0.5 multiplied by 64 plus 0.3 multiplied by 58 plus 0.2 multiplied by 55 equals 60.4, which is approximately equal 60. The last requirement is to calculate the forecast for week 6 using exponential smoothing with a smoothing constant of 0.4. Known that the forecast for week 5 was 59. Applying the exponential smoothing equation, F6 equals F5 plus alpha multiplied by A5 minus F5. This equal 59 plus 0.4 multiplied by 64 minus 59. This equals 61. Let us solve another problem. A cosmetics manufacturer's marketing department records during the last 6 months indicate the demand for a product as shown in this table. Predict the number of requests for month 7 using each of these methods. Naive. A 4-period moving average. A weighted average using weights of 0.4, most recent, 0.3, 0.2 and 0.1. Exponential smoothing with alpha equals 0.3. Use 1220 for month 6 forecast. Again, the plotted data shows that variations around an average exist, and there is no trend or cycles. So, let us move to the next step to make the forecast using different techniques. The first one is to make the forecast using the naive approach. Since the data vary around an average, so, the forecast for month 7 equals the actual demand in month 6, or F7 equal A6. So, F7 equal 1260. The second requirement is to calculate the forecast for month 7 using the 4-period moving average. This means using the most recent 4 months, which are 6, 5, 4, and 3. So, F7 equals A6 plus A5 plus A4 plus A3 divided by 4. This equals 1260 plus 1086 plus 1280 plus 1206 divided by 4 equal 1208. The next is to calculate the forecast for month 7 using a weighted average using weights of 0.4, 0.3, 0.2 and 0.1. The highest weight is assigned to the most recent period, which is month 6, the weight of 0.3 for the previous period, month 5, the weight 0.2 for the previous period, month 4, and the lowest weight is for month 3. So, F7 equals 0.4 multiplied by A6 plus 0.3 multiplied by A5 plus 0.2 multiplied by A4 plus 0.1 multiplied by A3. Substituting by the values of A6, A5, A4, and A3. F7 equals 0.4 multiplied by 1260 plus 0.3 multiplied by 1086 plus 0.2 multiplied by 1280 plus 0.1 multiplied by 1206 equal 1206.4 approximately equal 1206. The last requirement is to calculate the forecast for month 7 using exponential smoothing with a smoothing constant of 0.3. Known that the forecast for month 6 was 1220. Applying the exponential smoothing equation, F7 equals F6 plus alpha multiplied by A6 minus F6. This equal 1220 plus 0.3 multiplied by 1260 minus 1220. This equals 1232.
The next two problems show you how to make the forecast using data having trend.
The first problem. The demand data for the previous 9 periods are given in this table. Plot the data on a graph, and verify visually that a linear trend line is appropriate. Develop a linear trend equation for the following data. Then use the equation to predict the next 2 values of the series. Let us start solving by plotting the data. From the graph it is clear that the data are increasing with a linear trend. To develop the linear trend in the form ft equal a plus bt, we have to find a and b using these 2 equations. To do this, 2 more columns should be added to the table. One contains t to the power 2 and the other contains t multiplied by y. So, calculate t to the power 2 and t multiplied by y for each period. After that, add a new row at the bottom contains the summation of each column. Calculation of sigma t result in 45. Sigma y is 488. Sigma t to the power 2 is 285. And sigma t multiplied by y is 2545. We know that n is the number of periods. In the current problem it is 9. Well, substitute in the equation of b. b equal 9 multiplied by 2545 minus 45 multiplied by 488 all divided by 9 multiplied by 285 minus 45 multiplied by 45 equal 1.75. Now, substitute in the equation of a equal 488 minus 1.75 multiplied by 45 all divided by 9 equal 45.47. Known the values of a and b enables us to construct the trendline equation to be ft equal 45.47 plus 1.75 t. Now we can use this equation to calculate the forecast of the coming 2 periods, which are period 10 and 11. To find F10, substitute in the trend equation by t equal 10. So, F10 equal 45.47 plus 1.75 multiplied by 10 equals 62.97 approximately equals 63. So, the forecast of period 10 is 63. Similarly, F11 equal 45.47 plus 1.75 multiplied by 11 equals 64.72 approximately equals 65. So, the forecast of period 11 is 65. Let me now show you how to solve such problem using Microsoft Excel. Open new Excel file and copy the given data in the spreadsheet. To plot these data, select them, then select the Insert menu. In the ribbon look for the scatter icon, here it is, and click the little arrow to the right. Another menu will appear to you. Select the top left option, which is scatter. I will do some modification to make the graph looks better, by changing the y-axis scale, adding titles to the chart axis, removing the chart legend and the chart title. Yes, Looks better. As we concluded before, the data are increasing with linear trend. Microsoft Excel has a great option to find the appropriate trend line and directly find its equation. Let us do this. Simply click the plus sign to the right of the chart. A pop-up menu will appear, and at the bottom of this menu there is the trend line option. Check this option. You see the proposed trend line is added to the graph. Go back to the pop-up menu, move the mouse over the trend line option. An arrow will appear at the right. Click this arrow to see another pop-up menu. Select more options from this menu. A new menu will appear to the right of the sheet. Contains 3 different tapes. The first one is used to format the trend line. The second is used to add effects to the trend line. While the third contains the trend line options. Select this one. Here we can select the trend line equation type. The linear equation is the default one, but you can select any according to the shape of the graph represents your data. We will keep it as it is and scroll down and select Display Equation on Chart. Amazing, here is the equation. We obtain it with a few clicks without any calculation. Now, we can use this equation as before to calculate the forecast for periods 10 and 11 as before. Another way to find the coefficients of the linear equation is to use the scientific calculator. I will demonstrate this method using Casio FX991ES Plus calculator. We need to work in the statistics mode. To switch to this mode, press Mode button. This menu will appear. Statistics mode is number 3, so press the 3 button. We need to work with the linear equation y equal a plus bx, which is number 2, so press the 2 button. 2 columns will appear to you to enter different values for x and y. Let us start with x. Enter values from 1 to 9. Press the 1 button then equal button. Press the 2 button then equal button. Press the 3 button then equal button. And so on until x equal 9. Then using the arrow key to switch to the y column to enter the y values. The first value of y is 44, so type 44 then press enter. The second is 52, so type 52 then press enter. And so on until we enter the 9 values of y. Once finish entering the data, we need to store then by pressing the AC button to store and process the data. To find the values of A and B, press Shift then 1 to view this menu. The regression is number 5, so hit the 5 button. To obtain the A value, press 1 then equal. Of course, we got the same value of 45.47. Press Shift 1 again, then 5 after that 2 to obtain the value of B. Hit equal. The value of B is 1.75. Well, with these few steps you can easily find the coefficients of the linear equation without need to do many calculations. Let us solve another example using Microsoft Excel and the calculator. Freight car loadings data for 18 weeks at a busy port are as follows. Determine a linear trend line for expected freight car loadings. Use the trend equation to predict expected loadings for weeks 20 and 21. The manager intends to install new equipment when the volume exceeds 800 loadings per week. Assuming the current trend continues, the loading volume will reach that level in approximately what week? Let us start solving. Open new Excel file and copy the given data in the spreadsheet. To plot these data, select them then select the Insert menu. In the ribbon look for the scatter icon, here it is, and click the little arrow to the right and select Scatter. Modify the graph to looks better, by changing the y-axis scale, and adding titles to the chart axis. Yes, looks better. The graphical presentation of the given data shows that it is increasing with linear trend. Now, let us add the trend line and its equation. Simply click the plus sign to the right of the chart then check the trend line option. You see the proposed trend line is added to the graph. Hover again over the trend line option and then click this arrow to see the pop-up menu. Select more options from this menu. In the new menu appeared to the right of the sheet, select third tape. Scroll down and select Display Equation on Chart. Amazing, here is the equation. We obtain it with a few clicks without any calculation. The equation is y equal 18.996x plus 208.48. Let us try the scientific calculator to find the coefficients of the linear equation. Switch to the statistics mode by pressing Mode button, then the 3 button, then the 2 button. Now enter the values of x. Enter values from 1 to 18. Press the 1 button, then equal button. Press the 2 button, then equal button. And so on until x equal 18. Then using the arrow key to switch to the y column to enter the y values. The first value of y is 220, so type 220 then press enter. The second is 245, so type 245 then press enter. And so on until we enter the 18th values of y. Press the AC button to store and process the data. After that press Shift then 1 then hit the 5 button. To obtain the A value press 1 then equal. Of course, we got the same value of 208.48. Press Shift 1 again, then 5. After that 2 to obtain the value of B. Hit equal, the value of B is 18.996. So, the required trendline equation is FT equal 18.996T plus 208.48. We solved the first question by determining the trendline equation. The second question is to use the trend equation to predict expected loadings for weeks 20 and 21. Well, let us substitute by T equal 20 to find the forecasted or expected loading for week 20. F20 equal 18.996 multiplied by 20 plus 208.48 equal 588.4 approximately equal 588. So, the expected loading of week 20 equal 588. The same for week 21, substitute by T equal 21 to find the forecasted or expected loading for week 21. F21 equal 18.996 multiplied by 21 plus 208.48 equals 607.4 approximately equals 607. So, the expected loading of week 21 equals 607. The third question is: the manager intends to install new equipment when the volume exceeds 800 loadings per week. Assuming the current trend continues, the loading volume will reach that level in approximately what week? Here we have FT and it is required to find T. Using the same equation, substitute FT by 800. So, 800 equal 18.996 multiplied by T plus 208.48. Solve this equation for T results in T equal 31.1 approximately equal 31. The loading is expected to reach 800 in week 31.
Here, a problem is solved using the trend-adjusted exponential smoothing model. Before starting the first problem, if you did not do yet, subscribe and activate the alarm to be notified of the new videos. The data on new checking accounts at Fair Savings Bank are tabulated here. Use trend-adjusted smoothing with alpha equals 0.3 and beta equals 0.2 to smooth the new account data. What is the forecast for period 16? We know from the fourth video of this series that PAFD plus 1 equal ST plus TT, where ST is the previous forecast plus smoothed error, and can be calculated by this equation. ST equal TAFD plus alpha multiplied by AT minus TAFT, while TT is the current trend estimate, and can be calculated by this equation. TT equal TT minus 1 plus beta multiplied by TAFD minus TAFD minus 1 minus TT minus 1, where alpha is the smoothing constant for average and beta is the smoothing constant for trend. To solve this problem, we have to start by computing the initial trend estimate for period 5, T5. This can be done by calculating the average of the net change of the first 4 periods as follow. D5 equal A4 minus A1 divided by 3 equal 228 minus 200 divided by 3 equal 9.33. Next, we use this value of T5 to calculate TAF5 as follows. TAF5 equal A4 plus D5 equal 228 plus 9.33 equal 237.33. Now we can calculate S5, where S5 equals TAF5 plus alpha multiplied by A5 minus DAF5. So, S5 equals 237.33 plus 0.3 multiplied by 235 minus 237.33 equal 236.63. Known S5 and T5, we can calculate TAF6. So, TAF6 equals S5 plus D5 equal 236.63 plus 9.33 equal 245.96. Let us now retabulate the data and add 3 more columns for TAFT, ST, and TT. Now let us complete this table until period 15. Well, S6 equal TAF6 plus alpha multiplied by A6 minus DAF6 equal 245.96 plus 0.3 multiplied by 232 minus 245.96 equal 241.77. And D6 equal T5 plus beta multiplied by TAF6 minus DAF5 minus D5 equal 9.33 plus 0.2 multiplied by 245.96 minus 237.33 minus 9.33 equal 9.19. So, TAF7 equals S6 plus D6 equal 241.77 plus 9.19 equal 250.96. S7 equal TAF7 plus alpha multiplied by A7 minus TAF7 equal 250.96 plus 0.3 multiplied by 248 minus 250.96 equal 250.07. D7 equal T6 plus beta multiplied by TAF7 minus DAF6 minus D6 equal 9.19 plus 0.2 multiplied by 250.96 minus 245.96 minus 9.19 equal 8.35. TAF8 equals S7 plus D7 equal 250.07 plus 8.35 equal 258.42. Continue in the same way to find the values of TAF, S, and T for all 15 periods. After that, use the values of S15 and T15 to find TAF16. Where TAF16 equals S15 plus T15 equal 301.25 plus 5.98 equal 307.23. So the forecast for period 16 using the trend-adjusted smoothing is 307.23. Hopefully, you can apply this method by yourself. Here, 3 different problems are solved based on seasonality technique. Before starting the first problem, if you did not do yet, subscribe and activate the alarm to be notified of the new videos. Let us start with the first problem. The data in the following table represents the volume of calls received between 9 and 10 a.m. for 21 days. Calculate the seasonal relative for each day for that hour using the simple average method. In this problem, the seasons are the days. To solve such problem, we have to do 3 steps. The first step is to calculate the seasonal average. In this case, the average of each day. The average of Tuesday is 67 plus 60 plus 64 divided by 3 equals 63.667. The average of Wednesday is 75 plus 73 plus 76 divided by 3 equals 74.667. And so on till the calculation of the average of Monday. The second step is to compute the overall average. That is equals 63.667 plus 74.667 plus 84.667 plus 97.667 plus 88 plus 40 plus 52.333 divided by 7 equals 71.571. The last step is to calculate the seasonality relative for each day by dividing the average of each day by the overall average. So, the seasonality relative of Tuesday is 63.667 divided by 71.571 equals 0.8896. The seasonality of Wednesday is 74.667 divided by 71.571 equal 1.0432. Continue in the same way to find the seasonality relative for all days. The second problem. The following equation summarizes the trend portion of quarterly sales of condominiums over a long cycle. Sales also exhibit seasonal variations and the seasonal relatives are shown in the following table. Using the given information, prepare a forecast of sales for each quarter of next year, and the first quarter of the year following that. As stated in the trend equation, T equals 0 at the first quarter of last year. It is required to find the forecast for the next year and the first quarter of the following year. So, we need to find the values of corresponding T. The following table will help us. For the last year, D equals 0 for the first quarter. So, D equal 1 for the second one, D equal 2 for the third one, and T equal 3 for the fourth quarter. For this year, D equals 4 for the first quarter, D equal 5 for the second one, D equal 6 for the third one, and T equals 7 for the fourth quarter. While for the next year, D equals 8 for the first quarter, D equal 9 for the second one, D equal 10 for the third one, and T equal 11 for the fourth quarter. And for the following year, T equal 12 for the first quarter. So, we will use D equal 8, 9, 10, 11, and 12 to compute the forecast for the next year and the first quarter of the following year. Substitute with these values of T in the given trend equation. F8 equal 40 minus 6.5 multiplied by 8 plus 2 multiplied by 8 to the power 2 equal 116. F9 equal 40 minus 6.5 multiplied by 9 plus 2 multiplied by 9 to the power 2 equal 143.5. F10 equal 40 minus 6.5 multiplied by 10 plus 2 multiplied by 10 to the power 2 equal 175. F11 equal 40 minus 6.5 multiplied by 11 plus 2 multiplied by 11 to the power 2 equal 210.5. F12 equal 40 minus 6.5 multiplied by 12 plus 2 multiplied by 12 to the power 2 equal 250. Now, using the given seasonality relatives. The forecast for the first quarter of next year equal 116 multiplied by 1.1 equal 127.6 approximately equal 128 unit. The forecast for the second quarter of next year equal 143.5 multiplied by 1.0 equal 143.5 approximately equal 144 unit. The forecast for the third quarter of next year equal 175 multiplied by 0.6 equal 105 unit. The forecast for the fourth quarter of next year equal 210.5 multiplied by 1.3 equal 273.65 approximately equal 274 unit. And the forecast for the first quarter of the following year equal 250 multiplied by 1.1 equal 275 unit. The summary of the answer is illustrated in this table. The third problem, the first table shows a tool and die company's quarterly sales for the current year, while the second table shows the seasonality relative of the 4 quarters. What sales would you predict for the first quarter of next year? As we learnt before, the given data should be deseasonalized. Applying this, the deseasonalized sales of the first quarter is 88 divided by 1.1 equal 80. The deseasonalized sales of the second quarter is 99 divided by 0.99 equal 100. The deseasonalized sales of the third quarter is 108 divided by 0.9 equal 120. The deseasonalized sales of the fourth quarter is 141.4 divided by 1.01 equal 140. Well, the deseasonalized data for the 4 quarters are 80, 100, 120, and 140. Obviously, it has a trend. The sales of any quarter is 20 units more than the previous one. So, the trend forecast for the first quarter of the next year would be 140 plus 20 equal 160. To obtain the forecast for this period, we have to multiply the trend forecast by the seasonality relative. So, the forecast of the first quarter of the next year equal 160 multiplied by 1.1 equal 176. After solving these problems, hopefully, you can apply the seasonality technique by yourself. If you need more details, do not hesitate to contact me. Recalling the forecasting steps explained in the first video, the step number 6 is to monitor the forecast. So, here you will learn how to calculate the forecasting accuracy. But before going for this, let me ask 2 questions. The first question is why forecasts are not accurate? While the second question is why we need to calculate the forecasting accuracy? The answer of the first question is that forecasting is a real-world variable, contains random variations leading to some residuals. So, it is almost impossible to correctly predict future values of those variables on a regular basis. The answer of the second question is, decision makers include forecasting accuracy along with the cost when choosing among different techniques. Let us now define the forecast error and know how to calculate the forecast accuracy. As any other variable, the forecast error equals the difference between actual demand and the forecasted one for a certain time period and mathematically can be expressed with the shown equation. There are 3 different measures for forecast accuracy. They are, The mean absolute deviation or MAD, the mean squared error or MSE, and the mean absolute percent error or MAPE. MAD is the average absolute error and can be calculated using this equation, while MSE is the average of squared errors and can be calculated using the shown equation. And MAPE is the average absolute percent error and can be computed using the following equation. Let us use these equations by solving an example. The shown table present the actual and forecasted number of accounts serviced during 8 periods. Calculate MAD, MSE, and MAPE for this data. Add another 4 columns to the given table to calculate the error, its absolute value, its square value, and the absolute percent error for each period. For the first period, the error equals 217 minus 215 equal 2. Its absolute value is 2 as well, and its square is 4. While the absolute percent error equals 2 multiplied by 100 divided by 217 equals 0.92. For the second period, the error equals 213 minus 216 equal -3. Its absolute value is 3 and its square is 9, while the absolute percent error equals 3 multiplied by 100 divided by 213 equals 1.41. Continue in the same way till period 8. Now add a new row at the end of the table to calculate the summation of the absolute values of the errors, the square values of the errors, and the absolute percent errors. Using the previously given equations, MAD equals sigma the absolute values of the error divided by the number of periods, n, equals 22 divided by 8 equal 2.75. MSE equals sigma square values of the error divided by n minus 1 equals 76 divided by 7 equal 10.86. While MAPE equals sigma e multiplied by 100 divided by a, all divided by n equal 10.26% divided by 8 equal 1.28%. From a computational standpoint, the difference between these measures is that MAD weights all errors evenly, MSE weights errors according to their squared values, and MAPE weights according to relative error. One use for these measures is to compare the accuracy of alternative forecasting methods. For instance, a manager could compare the results to determine which one yields the lowest MAD, MSE, or MAPE for a given set of data. Another use is to track error performance over time to decide if attention is needed. Is error performance getting better or worse, or is it staying about the same? After learning how to calculate the forecast accuracy, let us learn how to monitor a forecast. But before this, we should know what are the sources of forecasting errors. Forecasting error may be due to inadequate model. Irregular variations may occur due to severe weather or other natural phenomena, temporary shortages or breakdowns, catastrophes, or similar events. Or random variations. That is the inherent variation that remains in the data after all causes of variation have been accounted for. A forecast is generally deemed to perform adequately when the errors exhibit only random variations. Hence, the key to judging when to re-examine the validity of a particular forecasting technique is whether forecast errors are random. If they are not random, it is necessary to investigate to determine which of the other sources is present and how to correct the problem. A very useful tool for detecting non-randomness in errors is a control chart. Errors are plotted on a control chart in the order that they occur, such as the one depicted in this figure. The center line of the chart represents an error of 0. Whereas, the two other lines, one above and one below the center line. They are called the upper and lower control limits because they represent the upper and lower ends of the range of acceptable variation for the errors. In order for the forecast errors to be judged in control, i.e., random, two things are necessary. One is that all errors are within the control limits. The other is that no patterns, for example, trends, cycles, non-centered data, are present. The following figures illustrate some examples of non-random errors. Here we have a point beyond a control limit, so the error is not random. In this case, the error has a trend. So, it is not random. While here, the error has a cyclic nature. So, it is non-random. The last case, if too many points on one side of the center line, the error is biased. Consequently, it is non-random. To construct a control chart, first compute the MSE. The square root of MSE is used in practice as an estimate of the standard deviation of the distribution of errors. That is, S equals square root of MSE. Control charts are based on the assumption that when errors are random, they will be distributed according to a normal distribution around a mean of 0. Recall that for a normal distribution, approximately 95.5% of the values, errors in this case, can be expected to fall within limits of 0 plus or minus 2s, i.e., 0 plus or minus 2 standard deviations, and approximately 99.7% of the values can be expected to fall within plus or minus 3s of 0. With that in mind, the following can be used to obtain the upper control limit and the lower control limit. Example for the calculation of the upper control limit and the lower control limit. Calculate 2s the upper control limit and the lower control limit, the data given in the previous example. In the previous example, the MSE was calculated to be 10.86. So, the upper control limit equals 0 plus 2 multiplied by the square root of 10.86 equals 6.56. For the lower control limit equals 0 minus 2 multiplied by a square root of 10.86 equal negative 6.56. Let us now solve two problems. The manager of a large manufacturer of industrial pumps must choose between two alternative forecasting techniques. Both techniques have been used to prepare forecasts for 6 months. Using MAD as a criterion, which technique has the better performance record? We know that MAD equals the submission of the absolute values of the errors divided by the number of given data, n. So we have to calculate the error and its absolute value for each technique using the given data as shown in this table. After that, compute the submission of the absolute value of errors. After that, calculate the MAD for each forecasting technique. For the first technique, MAD1 equals 28 divided by 6 equal 4.67, and for the second technique, MAD2 equals 34 divided by 6 equal 5.67. Obviously, the MAD for the first technique is lower, so its performance is better than the second one. The second problem. Given the demand data that follow, prepare a naive forecast for periods 2 through 10. Then, determine each forecast error, and use those values to obtain 2s control limits. If demand in the next two periods turns out to be 125 and 130, can you conclude that the forecasts are in control? As you know that the naive forecast for a certain period equals the actual demand of the previous one. So, the naive forecast for periods from 2 to 10 is shown in this table. MSE equals the summation of the square of the errors divided by n-1. So, we have to calculate the error and its square for each period as illustrated in the following table. Now calculate sigma e to power 2. Then MSE equals 150 divided by 9 minus 1 equal 18.75. Now calculate s that equals the square root of MSE, so s equals square root of 18.75 equal 4.33. For 2s, the upper control limit equals 0 plus 2s equals 2 multiplied by 4.33 equal 8.66. And the lower control limit equals 0 minus 2s equal negative 2 multiplied by 4.33 equal negative 8.66. So, the control limits are plus or minus 8.66. The forecast for period 11 was 124. Demand turned out to be 125, for an error of 125 minus 124 equals plus 1. This is within the limits of plus or minus 8.66. If the next demand is 130 and the naive forecast is 125, based on the period 11 demand of 125, the error is plus 5. Again, this is within the limits, so you can conclude the forecast is working properly. Well, this is the end of this topic. Hope you understand it. Contact me for any query and keep following us to learn more engineering topics, and do not forget to subscribe and activate the alarm to be notified of the new videos. See you again.